Protogalaxy. Okay. Why are folding schemes useful? What do you mean as a folding scheme? So, back in the bad old days of 2021, if you wanted to do recursive precomposition, you had a problem. So basically, you have a circuit, it could be a SNARK, could be a STARK, whatever, and you want to verify proof of correctness of another circuit in that circuit, and on you go. This is kind of an abuse of the word recursion. More accurately, it's kind of incremental verifiable computation. So you have some kind of SNARK circuit that updates some business and state. Then you have another SNARK circuit that takes up from that and modifies the state, and then on you go. Ideally, the circuits can all be different instances. Don't have to be the same algorithm. And the idea is that you can verify the correctness of the state by verifying the final proof. So this requires verifying proofs instead of proofs. That's horrible, and generally it's been a very big problem, expensive. There are also ways of solving it. So Halo was one of the ways. So if you're working over SNARKs, you could use cycles of curves. You have curve A, curve B. Curve A is very terrible at verifying proofs over curve A, but it's very good at verifying proofs on curve B, and vice versa. Blah, blah, blah. So the reason why folding is very powerful is because it kind of cheats. So instead of verifying proofs, what you're doing is you're creating random linear combinations of circuit instances. So by that, in a very black box way. So Protogalaxy and Protogalaxy, they have the concept of a like a black box special sound protocol. Can't spell properly. Protocol. Yeah. So the idea is you have some relation R, SPS, where you have some witness, omega, and some input string phi, where you're going to say that phi and omega, they are in the relation R, if for all I in N, you have some mapping function F, where you apply Fi over omega, I believe I might be mixing some things out, equals 0. Effectively what this is saying is, imagine you have a SNARK circuit like honk, where you have a bunch of columns in an execution trace, and you're applying algebraic relations to every row where the relation of the columns is 0. This is a much more generic and general way of capturing that. So it captures things like R1CS, CC, custom algebraic constraint systems. You could write like some weird custom sigma protocol that verifies a brainfuck interpreter, and you could make it fit this kind of concept. And the idea is we're going to take instances, these bad boys, and we're going to fold them. So we're not even going to bother making proofs. And this is very useful because in modern previous systems, you're going to be using a combination of a polynomial interactive oracle proof and a polynomial commitment scheme to construct your proof. That requires computing polynomial opening proofs. If you're folding the actual instance statements themselves, you don't have to compute opening proofs as a prover. It's very nice, very efficient. So there's a bit of notation abuse in Protogalaxy, and I think it's also in Protostar in that they use the symbols phi and omega a lot in different contexts. So we're going to try and, I'm going to put this up here, I'm going to try and leave it here for the rest of the talk, where the idea here is that we have a concept of a committed relation that we work over. Where, just double check I'm not going to be messing things up. So we have some protocol, like the protocol is parameterized by some integers. So the idea is you have some committed relation with defined by integers, let's call them H, D, N, where N is the second side, D is going to be the algebraic degree of your relation, and H is the number of rounds. And so the idea is the prover will send the verifier messages, message MI. So we have H rounds, so I in 0 to H minus 1. And the verifier sends challenge back I. And on you go, like an endless argument. And the idea here is that we are going to define the set of commitments to the messages. So all of the commitments to and the unis, the commitment to the original input string. So So this is going to be this is like, so input string, I guess in more like less protocol paper language and more like engineers language, this is basically like pre-computed stuff that defines your circuit. So for example, for Plonk, your input string would be commitments to your circuit polynomials, so like QA, QB, QC, QM, Q1, Q2, Q3, QM, QC, and then all like the sigma permutation polynomials. They would all be like the input string, kind of things to them. And all of the RIs, this is now considered, we write this as omega, which is just brutal abuse of notation because omega is supposed to normally represent witnesses. And the idea is that the omega is a concatenation of all this stuff. So it's called a transcript, and it's like the it's a history of the communications the prover and the verifier are sending each other over the course of this special sound protocol that we want to leave relatively black box. So to kind of make this explicit in Plonk, what would this be? You would have, in your messages, you have commitments to your Y polynomials, W1, W2, W3. You get your challenges, beta and gamma. Then those would be part of the R vector. Then you have your commitment to your ground product polynomial Z, that would be your message. And then you get another challenge, and then that would be that. And then this commitment to the phi would be the search polynomials, Q1, Q2, Q3, QM, QC, sigma 1, sigma 2, sigma 3. Job done.
So the witness is in the phi, right?
Pardon?
The witness is in the phi.
No, the witnesses are in the messages.
Message, okay.
The message, well, committed witnesses.
Yeah, committed witness, yeah.
Yeah, so phi, the idea is phi is, everyone should be able to know phi. That's not secret. But we want commitments to them because we want this to be succinct. And, what was I going to say?
For R1 CS, it would just be the witness, right? Or do you have other stuff as well?
I do not know enough about. I think you need to transform RLCS into some kind of. Yeah, I think it might be just the witness. Maybe. It depends. If you want to fold multiple different R1CS circuits, then you need to actually have some commitments to the actual matrix descriptions. But if you're folding the same thing over and over again, it wouldn't be. Yeah. And so one way of thinking about this is the way I kind of reason about the transcript is I take a existing protocol like Plonk or Hyperplonk, and you run the international protocol in your head between the prover and the verifier up to the point where the verifier starts sending the prover challenges that represent polynomial evaluation points. Then you stop, and that's your transcript. Okay, so we have this committed relation, and we're just going to assume, okay, we have some nice way of proving that. We're going to say, okay, well, this mapping function over and over is 0. Yes, there is some way of proving this. We don't care for the purposes of Protogalaxy. I'm now going to add. So I need more space. Add a second definition. So the idea is these are the things we want to fold. What are we folding them into? Because we effectively want to create some kind of random combination of instances that preserves enough structure that we can still verify that every instance is correct. And for that we use a relaxed, randomized relation. R round. So we are going to say that our kind of like witness input tuple is going to be phi and omega and beta and E in R round, where the idea here is that because we are folding committed relations, we kind of we can just inherit these parameters H, D, and N. They aren't going to change, so H, D, N. And the idea is that beta is going to be a vector of field elements size of n, and E is an n. And the idea here is that what we're going to be saying is that for all I in actually no, not in no. We can actually use some put around here. So we're going to say that this is satisfied if for the sum of power I beta. I'm going to explain what power is in a bit. F I omega. If this equals E, then we say, okay, well, then basically we say we've got some interaction protocol between prover and the verifier will accept if this holds. where the power polynomial is a power polynomial. The idea is it's a polynomial that is used to make all of these little FIs randomly independent linearly independent from one another. And so it's basically just so power I basic. You can have different structures. This thing is kind of, it's more of the more messy structure, maybe the less efficient protocol is, but it still holds. So here I equals 0 to log n. I'm trying to remember how this works. So if actually no. So you have no. So I'm used to thinking about power polynomials as multilinear polynomials, but this is actually just a function. So the idea is power I beta is basically I. And if you've got some like proving system, if it turns out if you're committing to your transcriptive and multilinear polynomials, then you need to transform power I to some multilinear polynomial where this property holds. I can get into that later, but for the purposes of actually understanding the folding scheme itself, that's not. You can kind of leave this a bit black box. So, and I really didn't leave myself enough space. I should have been smaller. Okay, so. We can now actually get into the folding problem. So so I'm doing setup here. I'm kind of defining the boundary conditions. What are we assuming is true? What are we assuming we have? We know all of these relations. We have ways of proving them, and we have like circuit attestations that fit into these relation types. And you can massage Plonk and RCS and everything to work in some context.
What is the E here?
Pardon?
E.
E is an error term. So the idea is what we're going to do is we're going to be kind of combining multiple committed relations, so the instances, the transcripts of committed relations, we're going to be combining them into these relaxed randomized relations, and in doing so, we're going to be adding some kind of error term, because if you have two Plonk circuits and you just multiply them by random numbers and add them together, it's not going to equal 0. But the idea with Protogalaxy is that we are going to run a little interactive protocol between a prover and a verifier. It's called a folding verifier and a folding prover that will prove that instances have been folded correctly into an accumulator where the error term that's computed is accurate. So the idea is what we're going to do is, let's say we want to do k folding, which basically means we want to fold k instances so omega I, phi I in our CM into an accumulator instance, so we have omega phi beta E in R rand, and outputs. So, but yeah, that's the goal. So the idea is so we have some Protogalaxy protocol where the inputs are going to be these omega I equals 1 to k. And we're going to have omega phi beta E. So these are the inputs, and it's going to output, and the output will be a new randomized accumulator instance. So we're going to have, let's call it omega prime, phi prime, beta prime, E prime. And so the idea here is we're not really proving very much, because what we're saying is, as a prover, we're saying, all right, I've got a claim, and I have some instances here, and I have commitments to them. I'm going to give to you, and I'm going to claim they satisfy this relation, this black box relation. I'm not going to prove it, I'm just going to claim it. And I have an accumulator instance where I'm making a claim that this holds in my accumulator instance. And in the folding step, the verifier is not going to check any of that. What we're going to do is we're going to update this randomized accumulator instance to say that if this is true, and if this is true, we're going to compute a new randomized accumulator instance with a new error term, and therefore produce a new claim about some witness and input strings that will then later need to be proven. So the way that kind of the actors break out in folding schemes is you have a folding prover, which is the person that does what I just said, the folding verifier, which checks that correctness. Then you have a decider prover and a decider verifier. And the decider prover verifier are kind of the more they kind of more closely map to proven verifiers in a canonical, snark-based interactive protocol. And typically the decider prover and the folding prover are the same entity because they need to share a lot of information. So a bit of a problem with that. This also kind of limits the use cases of folding, because unlike recursion, with a recursive proof composition scheme, the idea is that you can, if you're like verifying proofs inside circuits over and over again, then the provers for each circuit can be different entities, and it's not too painful because the proofs are also synced, so you don't need to pass a huge amounts of information between all the provers. With folding schemes, that does not hold. So folding schemes are very useful for incremental verifiable computation. So take Aztec, for example, where, by the way, how much time have I got? Because right, okay, let's look at doors. So take in Aztec's architecture, for example, we have, so a user wants to send a transaction that executes a bunch of smart contract function calls, and we want that all to be privacy preserving. So the idea is no one knows what's going on, the databases are all encrypted. So the user needs to make a proof of correctness of that transaction execution locally. And the way that works is each function in a smart contract is its own little smart circuit. And we have some kind of this concept of a kernel circuit, which is basically, it's like you can think of it as like a very, very, very primitive miniature node, where it's kind of verifying the correctness of the function call. So the idea is you have kernel circuits that will verify proofs of function circuits, and this is a recursive structure, where if you have a transaction that executes multiple functions, you will have multiple function proofs and multiple kernel proofs, and they need to be composed recursively so that you only have one proof. So this is where you would use incremental verifiable computation in a context where there is only one prover, right? It's the same person making lots of proofs recursively, so it's fine to use a folding scheme. Similarly, things like ZKVMs, if you're making a block proof, well, that's very chunky, it's complicated. It's very helpful to split that out into multiple smaller circuits. That can all be proven in parallel, but chances are this prover is still going to be the same person, so it's fine for all these, that you have to translate that. The folding scheme requires lots of information to make these folding proofs. Right. Anyway, so this is the start of the protocol description. So we have these. So just to recap, we've got input randomized accumulator, input instances of our circuits we want to fold, and we have an output randomized accumulator. Before I actually dive into the actual protocol steps, it might be good to sort of pause some questions.
Zac, you mentioned like a proving or folding verifier and a decider, right?
Yeah.
Folding verifier verifies whether this folding is done correctly. What does the deciding say?
The decider checks that this holds, basically. So the idea is that what is this instance of RAM? It's a claim. It's saying I have commitments to witnesses, I have commitments to an input string, and I have challenges and I have error terms, and I'm making a claim that there exists some giant vector of stuff omega that such that when you compute the sum will equal E. But that's just a claim, right? And the folding verifier doesn't check that claim.
So what does the folding verifier check?
The folding verifier checks that. So let's think you have you'll have your starting state where you have an input randomized accumulator instance, where again it's just a claim, no one knows if it's true or not, and you have input committer relation instances. Again, they're just claims and no one knows they're true or not. And you have an output randomized event. You'll produce an output randomized accumulator instance. Again, no one knows if it's true or not. But there is what the folding verifier will do is they will lay confidence that if the output instance holds, if it's a member of this relation, if this holds, if that holds, then so if that holds and it holds for the input, so if the input and the output randomized accumulators are correct, then this is satisfied. So basically, for all of the relations that have been folded into that accumulator, you will know that they satisfy your original committer relation, so your original Snark circuit, PLOM, class 1CS, whatever it is. And so the idea is what you do is you start with an empty accumulator. So obviously that's verify returns true. There's nothing there. It's not proving anything. And you start folding these. You start folding circuit instances into that accumulator. And each time you fold, the variable is going to go, okay, well, if the previous accumulator was correct, and the current accumulator was correct, then everything that was folded in is also correct. And we know that at the very start, the accumulator was correct because there wasn't anything in it. And so if we know that if at the very end the decider says, all right, this accumulator holds true, like this relation satisfies, then if you have knowledge of that and you have knowledge that all the folding verifiers return true, then you also know that every single circuit that you folded into the accumulator has also been satisfied.
Wait, but the folding verifier just add stuff together, right? They don't check anything.
They do a bit of checking.
They do check.
They do some checking, yeah. But it's I'll I can get into that. As in, like, they don't check the circuits, they don't check these relations. What they check is under the assumption that the inputs are good, like the input accumulator is good, then the only way that the output accumulator relation will be satisfied is if the everything else folded is satisfied as well. I need a bit more space, but I don't want to move this off the board. So I might, sorry, I just might take a couple of minutes just to shrink this down a bit. So we're just going to say here that there's some tiny sum pi beta left pi. There we go. Good system. So what do we need to do? If we if we have this starting statement, we have a slight problem, which is that we need to create a randomized accumulator based out of our inputs and our new stuff that's been our new instances. But we have an old claim about an old accumulator using a challenge beta. But the problem here is that that challenge was generated. Well, the verifier doesn't know when that challenge was generated, and therefore has to assume that challenge was generated before the prover has computed the committed transcript, omega. And therefore, we cannot, we need to basically, we want to be able to convert all of these instances into like randomized instances that we can add into this. But they all need to use the same challenge. And that challenge can't be beta, because it was generated before the verifier was sent these commitments. So step one is we need to update beta. The idea here is that we know that for this instance here, this ought to hold. But what we want to do is, so what we're going to do is, step one is the prover is going to compute a low-degree univariate polynomial f, where f of x is going to be equal to, let me see if I can remember this, how I beta plus x. Am I missing? Sorry, I need my reference material. I might be missing something. Give me a second. Yeah, I'm missing something. Okay, there we go. I thought it was. There's a new challenge here, delta. I hate it when people explain protocols to me and then just challenges pop out of nowhere. I really hate it, and I'm just not the same. So we're going to check that this. Okay, so step 0. Verifier generates delta in f to the log n. So yeah, delta, beta, there, vector challenges. What are we doing here? Well, the idea here is that we want to change the value of beta to something which is new, incorporates randomness that was generated after the prover was sent all of these new instances of code. And so we're asking the prover to make this univariate polynomial. So we have techniques that basically done in linear time, and what this does is the verifier can check that, well, if this is computed correctly, if computed correctly, f of 0 will equal e. So what happens is the verifier gets the prover to send then the coefficients of f of x, all the coefficients except the first one, because it needs to be e. So the prover sends the verifier all but first coef. I'm running out of space. Coef. Yes.
Why is f of 0 0?
It's e.
Right?
Because if x is 0, then this is just the original randomized relation statement, so it ought to be e, or someone's cheating, or they're making mistakes.
Question. Should
Yeah.
this be 0 or e, this relation?
Oh my god, yes, thank you. Good spot. Yeah, let me use e. Okay. So, what does that mean? What does this do? Well, this is nice, because now the verifier, so step 2, verifier generates another challenge, alpha in f, and we compute beta star I'm going to change it to star. So the Protogalaxy uses stars. Star equals beta plus alpha delta. So now, ta-da! We now have a new vector challenges that they're all completely linearly independent from the old challenges, and so we're now going to use beta star for the rest of our following steps. Can this be flipped around, by the way?
No, it can't.
So now the hard part. The hard part is we need to compute some kind of relation which combines these and these in a way which doesn't destroy information. And okay, I'm just going to have to get rid of this. Sorry. So, what's step 3? Step 3. Computation. So P computes G of X. G. Horrible G coming on. This is the nasty bit. As in nasty is in here, we'll implement it. This is the hard part. And the expensive part. So G of X is going to be a fancy polynomial. Again, it's low degree univariate because it's going to be the degrees are going to be log of n, so not that much information. That's going to be the sum. I equals 0 to n minus 1 of the power I beta star fi, and now here's where things get tricky. We have these are the Lagrange polynomials, I'll explain what they are in more detail. Omega plus the sum I equals 1 to k of li of x omega I. So, I've just thrown Lagrange polynomials in out of nowhere. We are using the Lagrange base for Protogalaxy because the Lagrange base is the best base. I'm not biased. So most cryptography papers, right? They have one trick. They have one cool trick that you apply to existing establishment techniques to provide something which is iterative and better and nicer. And the trick in Protogalaxy is that, unlike Protostar, so Protostar will not use the Lagrange basis. It'll be something very similar to this, but inside this f of I, you'll have like omega plus x omega I. So you'll use like a monomial basis, or coefficient basis. And under the coefficient basis, you're going to get a lot of error terms. And using the Lagrange base, it's very easy to cancel out those error terms. And what it means is that you can fold more than one instance into an accumulator efficiently. That's the trick. So what we have to do is, I kind of skipped over, we define a multi. I'm not actually sure it needs to be a multiplicative subgroup, but let's just say it is because it makes things good. Actually, no, we're not going to do multiplicative at all because we don't. I mean, in aspect we don't need a multiplicative subgroup. So we define a subgroup H of order k plus 1. So I'm not even sure subgroups are the wrong word because in Aztec we just use the integers 0, 1, 2 up to k. And so for Li of x equals delta I x, i.e. if x equals I, Li of x equals 1, if x is in H but without I, so it's in any of the other subgroup elements, then Li and x equals 0. So this is literally something like if you're using 0 and 1, then it's going to be well, like L naught is going to be like 1 minus x, and L1 is going to be x. So it's a lot of words to describe something fairly simple. Why are we doing this? What's the point? What's the purpose? Well, we're doing something really weird here, which is that if you think about what f is, these omegas are this transcript is it's kind of like like notation to be symbolic manipulation of a very complicated algebraic expression usually over multilinear polynomials. At least it's going to be. But even if you ignore polynomials, just imagine you have like just a bunch of vector. If you have a mental model of Snarks as you have a commitments to lots of vectors, and then you're applying relations overall. You're iterating over the vectors and applying relations to all the elements. Then all of those column vectors are kind of described in omega, And what we're doing is we're turning that relation over what was so these relations over field elements into relations over low-degree univariate polynomials. So for example, e.g., so we consider the Plonk arithmetic relation. So you have QMW1W2 plus Q1W1 plus Q2W2 plus Q3W3 plus QC equals 0. Well, now, instead of all these being field elements that you're iterating over, these are now degree k univariate polynomials. And so it means that the output of fi is no longer a field element, it's a low degree univariate polynomial. And so the sum of them all is a low degree univariate polynomial, and the goal is to compute it. Why is this important? Because if the original instances of the following are all true and correct, then G at, so let's say these subgroup elements are G0 to GK in H. Then G at G0 is going to equal how I beta star Fi omega. G at G1 is going to equal the same thing, but where Fi is going to be over 1, and so on and so forth. So the idea here is that we've produced a low degree univariate polynomial which combines all of the claims about all of the instances that we're folding with the accumulator claim. And so what's the verifier going to do? We need to check that this folding has been done correctly, because like I'll get into how and why in a bit, but the idea is if g of x correctly encodes all the claims that are represented by the instances, then g of x should be divisible by the vanishing polynomial of our subgroup. The idea is g of x divided by z of x is not a rational function if g of gi equals claim output. So it's instance. Okay, so gi is the so g naught is G naught is the output claim of the randomized accumulator, and then all the other GIs are output claims of the committed relations claims. That will only be true if g of x divided by z of x is not a rational function. So the idea is that there's no remainder term. Does that make sense? To both.
Wait, what do you mean by like claim output of instance again?
So what I'm trying to say is I'm out of space to read the right properly. So the idea is that if we evaluate G at every subgroup element, we're going to get we're going to get a claim about one of the instances we're folding. We're going to get a claim about randomized accumulator. The idea is G at G naught is going to equal E, our error term. G at G1 is going to equal 0. G at G2 is going to equal 0. G at GK is going to equal 0. And therefore, we've correctly accumulated the claims. And so what the rover is going to do is it's going to rewrite this in smaller form back there. X equals how I beta plus x delta fi omega. There we go. So the prover computes k of x, which is going to be equal to g of x divided by z of x. And by the way, z of x is just it's going to be an one product of x minus gi I equals 0 to k. So it's a vanishing polynomial because we validated every subgroup element equals 0. So the idea is this is going to be a very low degree polynomial. So small amount of data. P sends KX to the verifier. We need to commit or anything, let's get the coefficients. And check my source material. What are we going to do here?
KX is the quotient, right?
Yeah. No, I've done this wrong. I've done this all wrong. I've done this all wrong because this. Sorry, can I just wind back a little bit? This doesn't work. Because g of g naught is not 0; it's e. Therefore, this doesn't actually divide properly. The idea is for z of x to divide g of x, then g evaluated at every subgroup element has to equal 0, and g naught equals e. So we do. So we subtract off. Hang on. I'm gonna just write it the way the paper does because otherwise it'll just be a little bit confusing. Computes k of x such that g of x equals f of alpha L naught of x plus z of x k of x. So one way of thinking about it is k of x is you basically take f of alpha L naught of x and you subtract that from g of x and divide, and that will vanish. Actually no, sorry, I'm going to run it another way because g of x minus L naught of x f of alpha over z of x. So this divides properly because the idea is g at g naught ought to equal e. Alright, now what do we also know equals e? Well, f of alpha. The idea is that this polynomial we want to basically create a little polynomial which, when evaluated at g naught, equals e. So that's L naught of x times f of alpha. So we subtract that off of gx, and ta-da! Now all the roots align and we can divide. The prover sends k of x to verify. And so effectively, like when I was saying before, like the folding verifier is going to check that these claims are being accumulated correctly. This is the check. It's checking that this g of x polynomial correctly, like its roots all align with the claims about the instances that are being folded, and that every instance is going to equal 0. The sum of everything, basically equals 0, except the first one is going to equal e. And so, what does the verifier now do? Yes. Now we're basically done, more or less. The verifier will now will generate. So we have one last step to do, which is now we've got this like weird low degree univariate polynomial. This isn't like a instance we can prove, right? Like we're supposed to have our relations are supposed to have describing sums that sum to field elements. This is a sum that sums to a low degree univariate polynomial. That sucks. So we're going to compress that down to a point by generating a challenge gamma in f. Well, I really can't write. And v computes e. I believe. Hang on. Before I write this out, just going to make sure I'm not talking nonsense. Yeah. E equals g of alpha. No, not alpha. Gamma. Gah. Nearly have it. So the idea is, like, we have this relation, and that we want to check. We evaluated around the point, and now we have a claim about. So, like, what does this map to? This basically now we have a claim that the sum of power function of beta star times f I crit L naught of gamma omega plus I equals 1k L I gamma omega I equals E star. Yeah, E star. So this looks suspiciously like the claim of a randomized accumulator instance. So all we have to do to turn it into a randomized accumulator instance is the prover computes let me just check how I'm mixing up what the proof and the verify does. No, I'm not. Yeah, omega star, which is going to equal L naught gamma omega plus equals 1 k L I gamma omega I, and the verifier computes phi star, which is going to be L naught gamma phi plus I equals 1 k L I gamma phi I. And I've just realised now, I made a slight mistake when I was setting up my definitions at the start, and by slight I mean relatively large. So omega is not just defining like the committed instance. That's phi. Omega is actually is describing the witnesses. So it's like that's the raw data that you need to compute your proofs, to compute your for both the folding proof and the verifier. And phi is a committed version of the like the witness data and the instance data. And so the verifier now outputs phi star beta star u star, and the prover outputs omega star, and these that's your output accumulator instance. And yeah, the idea is if you run the decider algorithm on this, if you can verify that that claim is true, that implicitly verifies that the instances that you've folded into the accumulator are also true. Okay. Imagine it's impossible to read what I've written from back there. So I'm very sorry. But yes, I probably actually okay. Bit late now. I was bolted. I should have asked for it to open up the Protogalaxy. It would have been a bit easier to follow along, but not too late. So do you folks have questions about this? As in, I expect people to be very confused. I don't think I've explained it perfectly by a long shot. So, yeah.
I have a question. So, like practically, what is the advantage of folding k instances at one, like instead of just doing 2 at a time? Like, what amount of speed up do you get?
Instead of doing what at a time?
Instead of 2 at a time, like you're folding k instances at a time, right? So, like, what is the practical implications of that? Like, how much faster?
The practical implications is computing this doodad. No, not computing this doodad. So it's less hashing for one, because the idea is we're saying like the prover sends something to the verifier, and the verifier sends a challenge back. What's really happening is we're going to be using the Fiat-Shamir heuristic to turn this into a non-interactive protocol by hashing. And so running 2 instances of Protogalaxies or Protostar is going to be more hashing. There's also, think about this. There is, I think the amount of elliptic curve operations the verifier does is the same. So typically, what would like in a real protocol, the one thing I've kind of missed out here is I've said, the verifier computes phi star, which is this like linear sum. Well, if these are polynomial commitments, I'm saying I'll just make a sum of polynomial commitments. That kind of implicitly requires an additively homomorphic polynomial commitment scheme. The idea is you have 2 commitments polynomials, you can add them together, which basically means you're going to be using elliptic curves with current tech. And so this operation is going to require elliptic curve scalar multiplications. You need, actually, neither you need k plus 1 of these, but you can actually get mess with this formula and it's k scalar multiplications. I don't think so. If you do 2 instances of folding, then the verifier does a 1 extra scalar multiplication because they have 2 accumulators. The prover's also got to compute 2 g of x polynomials and 2 f of x polynomials. And my intuition is that the cost of computing 2 g of x polynomials with where k equals 1 is going to be more than the cost of computing 1. Actually, maybe that's not true. Yeah, I think the concrete differences are less hashing, a little bit less verifier work to do the scale multiplications, and less work to compute. You don't have 2 of these f of x polynomials to compute. And this is like a non-trivial amount of work to do as well. So slightly better.
And if you're developing this as a protocol, like how do you decide what k to use, or is it just as much that will fit in memory?
you implement your benchmark. So the tricky thing about this is that as k grows, the cost of computing this starts to grow very painfully. It grows like where the cost of doing this is going to be. I'm just going to go on. The cost is going to be O of roughly kn times c, where c is the cost of evaluating a single constraint in terms of field. So this is in terms of field work, field ops to compute GLX, and so generally c is going to be proportional to k, right? Because if I have a wait, is it? No, ignore me. It's not going to be proportional to k. I'm talking nonsense. But yeah, basically as k grows, you have this rather unpleasant term. It's technically it's linear in n, but it's with very painful constants. So, so no, it's k squared, isn't it? Yeah, my bad. No, it'd be nice if it was k. It's k squared. That's why it's bad. Yes.
And it is k squared because of the Lagrange polynomial that you're using, right? Otherwise, it would be.
No, even in univariate form, it's also k squared, because the idea is we have expressions over. You can actually say d. Is it? Because we are. Am I getting this right? It might be k and d. Hang on.
KD log KD.
Technically, it's kd log kd. Because okay, so you have some relation over univariate polynomials, and so you usually polynomial arithmetic. And so the asymptotically most performant way of doing that will be using fast Fourier transforms, which would be, have this k log k scaling factor.
Yeah.
But in general, with these small values of k, it's actually more efficient to do it the dumb, like schoolbook way of doing it os k squared. And so, if k starts getting to like 4 or 5 or 6, then this is going to start to really hurt. And that there is a section in the Protogalaxy paper later on, which is an alternative protocol for larger values of k, which removes this quadratic scaling factor. But yeah, you are right. It's k log k asymptotically, but the constants for small k's are bad enough that actually the k squared version is better.
But do we really care about saving on hashing from a practical perspective, because hashing comes so cheap? Hashing comes super cheap.
It's not that cheap. So hashing is cheap, but this whole protocol is cheap. So it's a good question, and it really depends on your use case and the resource constraints of your prover. If you have a relatively well-resourced, the resource constraints of your prover and the relative cost of the IBC algorithm compared to the circuits you're folding. So if I'm doing, if each circuit is like a million steps of a RISC-V VM, you're right. I don't care about this hashing. It's irrelevant. However, if the smaller each computational step becomes, the more this verified costs are going to dominate, because you're going to have to evaluate this folding verifier within a circuit as well. So it needs to be constrained. And if you think about what are the costs of the folding verifier, well, you've got to do a completely trivial amount of field arithmetic. It's basically nothing. It doesn't matter. And then you have hashing, and you have these elliptic curve operations you need to do. And normally the elliptic curve operations are kind of the bottleneck. But there are techniques that one can use to really crush down the cost of these. So there's cycle fold, which again it kind of uses folding techniques over the curve cycles to reduce the cost. And then you have Goblin plump, which is we've just finished implementing, which is it's basically a way. It's a relatively messy protocol, but it's a way of transforming the curve operations, which it's called like non-native, because the idea is if you're doing your proofs over a single curve, then the curve arithmetic you have to do to compute this is going to be over a prior field, which is not the natural field of your circuit. And so Goblin plump is a way of enabling you to recurse over the same curve over and over again, and all these curve operations are effectively deferred, they're delegated to, they're basically aggregated inside a big commitment of claims. You're basically saying, instead of the circuit evaluating elliptic curve multiplication, you say, here's the inputs, here's the claimed output. I'm going to put them in this table, and I'm going to move on with my life. And then the idea is as you recurse, as you fold, this table grows and grows and grows and grows, and then at the kind of end step of your recursion stack, you then run a different circuit which verifies this table, but there's a very cool trick you can do to run that circuit over the friendly elliptic curve, so over a different elliptic curve where these operations are very cheap. And the rough heuristic I'm using is that with Goblin Plonk you can sort of get the cost of a non-native scalar mul to about the cost of 2 native scalar multiplications, and that's very cheap indeed. And once you do that, and you have a trivial amount of field work to do, then the hashing actually starts to become a significant cost, even if you're using a smart-friendly hash algorithm. And just like for ASIC's use case, because we want these individual circuits, they represent function calls, which ideally can be quite lightweight. We really care about the cost of this verify algorithm. But yeah, if you're not in that regime, then the advantages of reducing hashing is not that much. Oh, one other thing. Sorry, I forgot to mention. This is assuming you're using smart-friendly algebraic hash algorithms. So the authors of the Protogalaxy paper are in the Liam. They are very much not SNARK algebraic hash maximalists. Basically, like if you think about like Poseidon, Rescue, all of those, the amount of kind of scrutiny and analysis that they've had is very, very low compared to like canonical random order hash functions like SHA-2, SHA-3. So the whole industry is using them. We're using them, but you were going to submit Poseidon to NIST and say, hey, let's standardize on this. They totally get lost because they'll be like, come back in 10 years, please. So if you do want to use proper random oracle hash functions, then obviously the cost of hashing will really dominate, and this becomes more relevant. Cool. So yeah, last chance for questions, fusions. Cool.
In the beginning, you mentioned something about folding schemes that they can't be parallelized, right? Like they can't be split into different.
You can parallelize them. You can't have different prover entities, because to make the folding proof and to make the decider proofs, you need omega, and omega contains all of your witnesses. And so for a big circuit, that's gigabytes of data. And so if you have different prover entities, you've got to get that to the different prover somehow, and that's even if you're okay sharing secrets, which you may not be. Like that's a lot of information, and so latency will be a big bottleneck.
So you can't fold like k instances of some protocol, k instances of the other protocol, and then somehow accumulate both of them. Like, is that possible?
No, because the idea is that the decider if you think about what we're folding, there are all claims about. I dropped it off the board. But there are all claims that you have this mapping function f that when you apply to your witnesses is going to equal 0 or some error term, and so that function f has to be consistent across all of the instances that you're folding for this to work. And so one of the very nice things about Protogalaxy and Protostar is that like f, it has to be the same protocol, but it doesn't have to be the same circuit within that protocol. So take, for example, Plonk. You can fold multiple different Plonk circuits into an accumulator, but you can't say fold Plonk and ARM and CS together in the same accumulator. You need different accumulators. Cool, well, I assume that's all cleared up and that everyone is now knowledgeable enough to implement Protogalaxy. Thank you.